These are the video notes for section 7.5, more trigonometric equations. What we're going to do today is actually just more solving like we did in 7.4. There'll be a little bit of a twist to that problem as we get to the second half of the notes today. But before we do that, let's kind of recap a little bit, talk about some of the similar problems from 7.4 where it's an algebra approach to start, or maybe it's got an identity approach, and then the difference between an interval of 0 to 2 pi and all solutions and how you write some of those answers, just to kind of recap those ideas with you guys. So hopefully when you look at this problem, your algebra brain kicks in and says you got a factoring by grouping problem going on. So we'll get the factoring by grouping started by taking out 2 cosine of x from the first two, negative 1 from the second two. Then we know we take out our common factor, which is in parentheses, and then a little bit of algebra solving, and we're ready to go. Now remember the question you ask yourself when you're trying to solve, because again we're solving for x, and also remind this is not an inverse question, so there's no restrictions on how you answer it, is the sine of what angle has a value of negative 1/2. Well, for starters, I know sine is negative in quadrants 3 and 4, and then that would be my pi over 6's, so I'd be going for 7 pi over 6 and 11 pi over 6. What angles have a cosine value of positive 1/2, while cosine being positive in quadrants 1 and 4. So again, I would answer that as pi over 3 and 5 pi over 3, and that's a value we used in the first part of 7.4. And we're going to use this one quite a bit, so we'll pop up again in a little bit. So here's the unit circle again, just to kind of talk about the all solutions concept. So I look at the sine negative 1/2, and I'm doing 7 pi over 6 and 11 pi over 6, and I ask you the question now. I haven't done one day of this. Is it one statement or two? It's two. They each need their own individual statement, because the only way you're getting back to 7 pi over 6 is by doing a multiple rotation of 2 pi. So I'm at 7 pi over 6. The only way I get back here coterminal is to come back around 2 pi and land that spot again, or negative 2 pi. Remember, all the k on the end does is provide a multiple. So if k is 1, 2 pi around. K is negative 1, negative 2 pi around, and k is 2, and so on. So as k gets bigger, positive or negative, you just add more rotations in each direction. But again, the reason I need two statements is because if I'm at 11 pi over 6, for example, let's say I start at 7 pi over 6, the question would be, could I rotate from 7 to 11 and then 11 back by the same amount? Well, this is clearly different than this. So you can't do one statement covers all solution possibilities. You've got to do one for this one and one for this one to get it going coterminal. And that's also going to be true for pi over 3 and 5 pi over 3 for the same reasons. So a little bit of algebra to get you going, factoring by grouping, and then interval 0 to 2 pi, and then all solutions. And remember, k is just the multiple. It gets you coterminal to the same location, which gives you another round of angles that have sine values of negative 1/2 or cosine of 1/2. Then also in the 7.4 notes, you remember we did one that had a little bit of an identity substitution idea going on. So today we're going to hit a 2x and a 3x, and we're going to hit a half, and we're going to talk about how this could affect it, but I'll explain the differences a little bit later on. But in this case, I see a doubling identity. This is a notes from 7.4, and I went off and used a doubling identity. For this problem, I see a half angle going on, and also the reason I know I got to do something with identity is because how would you start solving this, right? Let's say you try to move this stuff to the other side. How do you deal with this and this together? There's no factoring going on, so there's got to be some way to manipulate the problem. So the manipulation comes from me thinking about, all right, which identity could I use? I think one to me kind of stands out. I'll explain why I chose that one. The reason I'm choosing this one is because what I think I want to do now is multiply both sides by 1 plus cosine, which creates a Pythagorean identity on this side. And I know that's going to help start cleaning things up. Plus, a step down the road, it puts the entire equation into the same function. Had I used this one, I would have had to multiply through by the sine. And that would have had 1 minus cosine equals this times sine, and then all of a sudden that doesn't really make it that great to manipulate. So there's a little bit of having to pick which one's going to go the best for you. But what will happen here is these two will cancel. I'll get 1 minus cosine squared. And 1 minus cosine squared can then be replaced with sine squared. And then what I'm going to do is, again, start moving stuff around a little bit. So what I actually did was subtract the sine to this side, but then I just changed the order to have it read equals 0 at the back. Factor out a sine, and then start your solving process. So, solving, like a lot of other kinds of problems where we do solving of some sort, there's a lot of upfront work. The solving doesn't really happen actually all the way until down here, right? This is all just getting things ready to go. And then, ask yourself the questions on the interval 0 to 2 pi, where do you get these solutions? Well, the sine would be, what angles would have a sine value of 0? That'd be pi over 2 and 3 pi over 2. And what angles have a sine value of 1? That's pi over 2. Now, again, thinking about the all solutions idea, this is a good chance to talk to you guys about it one more time, one statement or two when I go to all solutions. For this, it can be done in one because, right, if I start at pi over 2 and I say let's rotate to 3 pi over 2, that's separation of pi, and then rotate back, that's a separation of pi. So literally I can just add multiples of pi and I'll keep hitting these two spots forever, positively and negatively. So in that instance I can say, all right, we only require one, which is pi k. A multiple of pi will rotate you back and forth, alternate you back and forth between these two answers. Now on the other hand, the pi over 2, where I'm sitting right now up here, that's got to be a 2k pi because there's not another spot. Where sine is 1, sine is only positive 1 here. And the only way I get back to this spot or go coterminal is I keep adding multiples of 2 pi. So it's 2 pi k there. Okay. So again, a little bit of manipulation to get going, and all of a sudden it becomes a factoring problem and you're back to your sort of standard algebra. So what I want to start doing with you guys now is talk about the difference between a basic function, trig equation that has 2x, 3x, or x over 2 in it. For example, we can do x over 3, we can do x over 4. And the one that I just showed you in the last slide, and also the one from 7.4. And the difference here is I'm going to have a basic function, and what the 2x, 3x is doing is actually changing the period. So if we just talk about this strictly as graphing, you guys know from your regular graphing from chapter 6 that a standard cosine or sine wave has a period of 2 pi. If I change the frequency to 2, now the period becomes pi. If I change the frequency to 3, now the period becomes 2 pi over 3. Well, what that means is the graph is going to cycle in a smaller space, and visually here's what's going to happen. So if I did a 2x, that's 2 cycles in a space of 2 pi, but it also means I hit my 1/2 line twice as often. So I have 4 solutions instead of 2. So 2 solutions in the interval 0 to 2 pi, and all of a sudden in the interval 0 to 2 pi, I should say, but with pi being the cycle, I'm going to get twice as many solutions. And then if I go 3x, for example, which is 3 times the cycling, so I have 3 cycles going on in 2 pi, well then I'm going to hit that half line 3 times as much, 3 times the solutions, as I would have compared to the graph of cosine of x. So if this has 2, this has 4, this has 6. What it means in general is this: exactly that number of solutions is what you get from x, 2x, twice as many, 3x, 3 times as many solutions, as you would have if you were doing just plain x. Now the other way we can go with this is we can make the period bigger. So if you think about the cosine of x over 2, well, that'd be a 4 pi period, which means here's the 4 pi cycle, and yes, I'm hitting the graph twice, but in a period of 2 pi, I've hit it once. So now I'm down to half the solutions. So in a span of 2 pi, I'm going to have half the solutions I would have in a span of 4 pi. And then 6 pi, which looks like this. And so in other words, to get my 2 solutions in the one full cycle through 6 pi, great, but in a period of 2 pi, I'm still going to pull off 1 solution. And then divided by 4 would be a period of 8 pi. And again, all we're doing now is stretching the period out. So it's taking a lot longer to hit that half line than it would in a normal period. And it's still only getting that 1 solution going on. So a couple things to point out on what these mean. So x over 2 means 2 solutions on the interval 0 to 4 pi, 2 solutions on the interval 6 or 8. What it also means, it's important when you're doing the WebAssign questions, and I'll point this out in a second, is that although you're going larger than 2 pi for period, if your question was about the interval 0 to 2 pi, you'd only have 1 solution. So you got to kind of watch out for that. And again, I'll show you that in a second. Okay, well that's, the visual. Let's get into some of the problems and show you what happens. Again, how do I know that I'm not doing a double angle identity? Because I have just the basic cosine function, nothing else is going to mess me up. So I can go ahead and just work with the 2x. What you do is your normal algebra getting started. We did the same problem in 7.4. The difference here is I treat it as though the 2x is just going to be an x for a moment. So essentially in my head, I'm kind of just covering this up going, well, what angles have a cosine value of 1/2? It's still pi over 3 and 5 pi over 3. And I still have the all solutions idea going on. The way I take care of the 2 or create the more solutions idea is I divide through by 2. And I divide through by 2. And now we're saying, okay, that's great. Now I've got x equals, that's actually my answer, my solution. And what are the answers? Well, you're going to start with pi over 6 for sure, and you're going to start with 5 pi over 6. Now remember, there were only 2 to begin with, pi over 3 and 5 pi over 3, and there should be twice as many, so that means 4. How do I get the others? Well, here's where your multiple finally comes in kind of handy to generate the other solutions. So what's the multiple in terms of 6? It would be 6 pi over 6. So I would start here and I would add. And that would create 7 pi over 6, and then same thing over here. The multiple is the same. Start at 5 and I would add. And by doing that, I'm generating the list of angles that would work on the interval 0 to 2 pi. And if you kept going, you would actually go outside of 2 pi. So if I went one more round of 6, that'd be 17. That's beyond 2 pi. If one more round of 6, that's 13. That's beyond 2 pi. So there's lots of ways to know I should stop, like I'm going outside of 2 pi, or I've hit my 4 solutions, and then here's visually what's happening. So when the period is expanded, the period, has been condensed, but I'm going all the way to 2 pi, then I'll hit it 4 times. Where here the period of pi, just hitting it twice, but twice as many solutions in 2 pi. Okay, let's try some others. So we're just going to kind of continue with this problem for a little bit, and we're going to do a 3x, and we're going to do an x over 2, and we're just going to keep showing you the difference of how that changes the problem. And really all it does, again, is add or reduce the number of solutions. Now a 3x is 3 times the solutions. So what I do is I keep imagining this as just plain x to start. When it's just plain x, I still have pi over 3 and 5, and then the way the 3 is taken care of is by division. You divide it out, and now it starts to show you where the solutions would pop up. So pi over 9, 5 pi over 9 would be my starters, but I know that there were 2 to begin with, which was pi over 3 and 5, and I should have 3 times as many, which is 6 solutions. So how do I generate the other 4 solutions? Well, I need to use my multiple, and this is where the all solutions comes in handy. So what I'm doing here is just getting 2 pi over 3, give it a common denominator in ninths, and then I'm going to start using that to create the rest of my solutions. So now what I do is I add 6, and then same thing over here. I just start at 5 and I add 6 till I can generate my solutions. So in this case, you really want, when you do a 2x, 3x problem where you're going to be increasing the number of solutions, you want to do the all solutions first. So you have this for 2 reasons. 1, where do I start? And 2, what is the multiple that's going to generate the rest of the answers? Okay, so now we're seeing 3 cycles in a space of 2 pi, so I'm hitting 3 times the answers in a space of 2 pi, which are these 6. All right, let's do one more with the x over 2. Just keep working the same problem over and over and over again, but just change the period on you guys. So I'm still working the half, so we can stick with those values. Again, for now, I just treat it as though it was a plain x, so I still say pi over 3 and 5 pi over 3. So cosine of what angles have a value of 1/2. And then the way I take care of a divided by 2 is to multiply through by 2. So now I'm multiplying through by 2. And then the all solutions, I'm going to say, all right, let's start with my first one, and what is my multiple, right? Well, here's the thing about this, is that the interval 0 to 2 pi in terms of thirds is actually 6 pi over 3. So let's say the multiple is 4 pi, which there it is in thirds, and I start to add, I'd be at 14. Okay, I'm well beyond 6. So this is it. And over here, there's nothing, because 10 actually is already beyond 6 pi over 3. We're already outside the range of 2 pi. So the thing about this one is, well, yes, you can get more solutions if you increase your period, but if the question is this, then you don't. You get, that's it, because look where 2 pi is at. Sure, if I went out further, yeah, I'd hit it, and I'd hit it, and I'd hit it, but this question specifically says on the interval 0 to 2 pi. So that'll be kind of the catch in WebAssign. You'll be cruising along doing this kind of stuff, and you'll miss maybe this. You'll start trying to crank out more answers, and it's like, well, wait a minute, you're already outside the range. So only one solution if we're on that interval. Okay. Last little bit of this here, we'll wrap it up. So we're just throwing in x over 4, just again to kind of show you guys some other things that can happen. Again, how I know to do this and not do identity, well, first of all, I don't have an identity for that, but also I have just a plain tangent function, so I can do the basic solving. You start the all solutions like you normally would, so you say, where is that happening? Now, reminder for you guys, why did I only use one solution, and why did I use pi k? Because 5 pi over 6 and 11 pi over 6, quadrants 2 and 4 are where tangent are negative, and they're separated by a rotation of pi. So if I was giving you the question one statement or two, tangents are always one statement for all solutions, because your solutions will be diagonally opposite quadrants, which puts them pi apart from each other. Then I get rid of that, divided by 4 by multiplying through by 4, and then on the interval 0 to 2 pi, there's no solution. Now, the simple reason for that is because this angle would be my starter angle, and it's already outside the range of 2 pi. And here's the visual to go with it. Here's the tangent graph in a period of 8 pi. I'm not even hitting the line until I get out to 10 pi over 3, which is what my first solution is. But on the interval 0 to 2 pi, which is here, nothing. So yes, there are solutions if you get the period, expand the period way out. But if this is the question, and this is my starter, you're already outside the range of 2 pi, because 2 pi is equivalent in thirds is 6 pi over 3. So some little things to watch out for, the 2x, 3x, x over 2, x over 3, x over 4 kind of stuff. Again, you got to decide. Go this route, like a period change or an identity. An identity will be because you've got it mixed with other functions, and you can't really just kind of do basic solving. And that's going to be it.